Hello, my name is Walter Swann and I'm going to take you through the presentation on fire engineering, testing, principles and practice. So I'm with you for about the next 20 minutes and what I'm going to try and cover is some of the background to advanced structural fire engineering. I am going to repeat one or two bits that you've already heard from the likes of John. And that's by design, so it's really just to try and reinforce one or two points. So a couple of subjects that I'm going to cover, related subject areas during the presentation. I'm going to investigate the traditional approach to protecting buildings and fire, and then move on to ways of developing fire precautions using newer engineered methods. And then I'll also cover some of the tests that were conducted to underpin those modern structural engineering, fire engineering methods. So you've seen this one before, but in a slightly different guise. I'm sure many of you are aware that the obligations placed on you and contractors to ensure that buildings are both safe and healthy are contained in the building regulations. And repeating something that John said, but the requirements of the regulations are set out in very simple functional terms. So they outline what you need to do, but don't necessarily tell you how to go about doing it. And that's seen here in the regulation which covers structural stability in the event of a fire. So fortunately for us, the government does publish guidance on how to meet the functional requirements of the building regulations, and it does so through the approved documents. So again, a document that you've already seen this morning. So approved document B, and it covers fire precautions in buildings. And amongst other things, it describes the fire resistance periods required for compartmentation and for elements of structure. And fire resistance periods are shown here in table A2. What this shows is that the fire resistance period is a function of two things. It's a function of the building occupancy, obviously, and also the building height. So if we take the case of an assembly building, between 5 and 18 metres would be there in the table, and we'd have to provide a fire resistance requirement of 60 minutes, whether it's sprinklered or not. If we then move occupancy class and take a look at an office, and in this case I've chosen one which is over 30 metres in height, the regulations tell us that we need to fire protect that for 2 hours, and that we also have to provide a sprinkler system. So the sprinkler system in that case is mandatory. Just looking at elements of construction that have to have a fire-resistant function. And they tend to fall into 3 categories, or they have to perform in one or all of 3 ways. The first one is a structural function. So in essence, the element has got to stay standing long enough for the people to evacuate the building and for the fire crew to start fighting the fire. The other element that they may need to perform, or the way that they might need to perform, is to prevent fire spread. So our compartment walls, compartment floors have to meet the requirements in that sense. And the third requirement is to actually resist heat transfer. So if we think about the elements that we might come across in a building, a floor slab in a typical multi-storey building would need to resist all 3. But a non-load bearing compartment wall would just need to meet the requirements for integrity and insulation. And a fire-resistant glass window might only have to resist integrity in terms of failure. So this is what we've been asked to achieve. And now what I'm going to do is take a look at fire testing. So if we've got a product that must have a fire resistance capability of some sort, how do we go about proving that? How, for example, do we establish what a steel beam protected to 1 hour's fire resistance can actually achieve in practice? Well, there are standards that describe the fire testing that must take place to provide fire resistance. There's a British standard, an ISO standard, and a European standard. And this is those 3 standards, or here they are. In theory, all 3 standards are pretty much the same. But in practice, because of different fuels and control mechanisms, they can give different results. But they all follow the same time-temperature curve, and the equation there on the slide describes that time-temperature curve, and this is what that time-temperature curve looks like. So that curve tells us a couple of things. First of all, it tells us that in a standard fire test, that the product being tested will be deemed to fail at either 30, 60, 90 or 120 minutes, depending on how far it goes along that curve. And that's when it's heated using this time temperature profile. Now in practice, this is an extremely severe fire test, and very few fires in real buildings will get to the sort of temperatures or last for the sort of durations shown by that time temperature curve. We also should note as well that the time temperature curve continues to increase in temperature as time goes on. And in practice, it's very, very difficult to achieve that. In fact, the only way that you can do that is if the fire brigade come along and actually pour petrol on the fire. So quite impractical in some respects. So this means that there's significant conservatism built into our fire regulations. And this is one of the reasons why it is rare for real buildings to collapse during a fire, despite Wilf's video clip earlier. This is what a standard fire test on a beam looks like. Almost as exciting as this presentation this morning, I think. But where does that leave us? Well, so far what we've learned is that if an element of construction requires a fire-resisting function, that it must be proven in a fire test, and that these tests are severe. The other thing that we've learned is that the most common source of information on fire precautions in buildings are published by the government in the form of the approved document, and that they are quite prescriptive. Those regulations are quite prescriptive. There's a little wrong with how we design precautions, fire precautions, in terms of the level of safety, as long as it's done properly. But if we look at the issue of structural fire resistance specifically, it must be said that we design for fire in a very conservative manner. We first of all design the frame, and then at some later stage during the design process, we include the fire resistance. So why do we do that? We don't do it for wind, which is what that graphic shows there. When we design for wind, we design the wind resistance into the building. It's part of the structure. If we design for wind in the same way that we design for fire, we'd do this by providing additional separate protection. And a little graphic to try and show that, which I hope you'll agree doesn't really make a great deal of sense. But it does have its parallels with how we design for fire. So this leads us on to the next part of the presentation, which introduces the possibility of moving away from those prescriptive methods given to us in the approved document and designing for fire in the same way that we design for everything else. And in doing so, we'll see how fire resistance can be designed into buildings. So another extract from approved document B, and again, no apologies, but I think you've seen this from John this morning. And what this clause does is it validates the use of engineered approaches to fire and goes a bit further by saying that in some buildings, an engineered approach to fire may be the only way to meet the requirements of the building regulations. So quite an important point that. So in other words, if you simply follow the prescriptive rules in the approved document, that might not be a safe building that you end up with for certain types of buildings. So fire engineering can be used to address problems with issues such as means of escape, smoke control, access for the fire brigade. However, for the purposes of this presentation, what we're going to concentrate on is structural fire engineering, so how the building stands up in a fire. And modern advanced structural fire engineering in steel frame buildings can be traced back to this event in 1990. So this is the Broadgate fire, a major fire in a composite steel deck building. Now, the interesting aspect to the fire was that it happened when the building was under construction. So not all of the fire protection on the steelwork was in place. So we had a semi-protected steel frame building. Now, everything that we knew at the time about how steel behaved in fires told us that this building kind of should have collapsed for the fire that took place. But it didn't. It actually showed great resilience and it stood up even in quite a serious fire. The other thing that we learned from this experience as well is that the repair costs, the costs of actually repairing the structure, weren't as significant as many people thought they might be. And I think it turned out that the repair costs, the structural repair costs, was only 5% of the total bill. So this is the aftermath of the fire and carnage, as you can see. But although there was significant damage, there was no collapse of the steel frame. So what this event suggested was that composite steel deck floors had great reserves of strength, more than was evident from the standard single element fire tests that we were accustomed to doing. The question was, how could we understand this and then make use of that in terms of design? It took a little while to get to this stage, but the steel industry didn't get to investigate that seed of a thought until 1994, when the BRE, the Building Research Establishment, British Steel, as they were then, built this 8-storey building at Cardington, and then tried to burn it down. So a series of fire tests were undertaken, 7 in total. And this slide kind of tries to give you a flavour of what those tests were. So different compartment sizes were looked at, different geometries, and that's really what this slide tries to get across to you. The largest of the tests, which is shown in green on this slide at the bottom left there, was a compartment which was 324 square metres in size. And this was, and probably still is, the largest natural fire test that's ever been conducted, a real fire test. The tests were severe, so I don't know if you can remember that time temperature curve, but temperatures on that time temperature curve were probably about 700, 800 degrees. In this fire, the temperatures reached 1200 degrees. So this was a very, very serious fire. And the temperatures that were sort of experienced in this fire aren't typical of real fires, and they don't even reflect kind of the time temperature curve that we use for elemental tests. So a very, very serious fire, and again, everything that we'd known at the time kind of suggested that this building should have collapsed, but again, it didn't. This is a view of the test just before the fire took place. So again, on most of the tests, we tended to use timber cribs as the fuel source, although there were plastics added for some of the tests to increase the rate of ignition and also to increase the maximum temperatures experienced, or that the structure would experience. Ventilation was played around with in some of the tests, but not in this particular test. So this is a short video of what a natural fire test looks like. And it's customary, as you saw, to send in your most expendable member of staff to light the fire and get it started. I don't know if you saw that at the beginning there, but the steel members were unprotected. So the only thing that was protected here were the columns. So the beams, and that's all of the beams, and the floor deck itself were left unprotected, so no fire protection to those at all. And I think what you're seeing here is the fire when it's reached the flashover point. So here, the fire was out of control, and if the fire brigade turned up with that, they wouldn't be trying to put the fire out. All they'd be trying to do would be to stop the fire spread. This is obviously after the fire, and we can see there that there's some extensive damage to the steelwork there. But the good news was the building actually kind of stood up. It didn't fail. So a couple of photos that kind of show you the aftermath of that fire. So things that we kind of learned along the way. So here we see some pictures of connections, and because there was some excessive, or not excessive, there was quite a lot of deflection in those floor slabs. We did get some distress shown in the connections here. So what you're seeing here is a bit of end plate fracture. Failures occurred in the weld, but that didn't occur during the fire. That actually occurred after the fire when the steel cooled. Again, just taking a look at some of the photographs from the fire. So what we're seeing here is a little bit of bottom flange buckling here. So during the fire, the steel would expand, and wherever the steel was kind of restrained, there would have been some buckling taking place. Bottom left here, we see there was a compartment here which has been removed afterwards. Steel had been protected to the left of that compartment, but within the compartment where the fire took place, no fire protection to the steel, so we've got a little bit of buckling taking place on the bottom flange there due to expansion during the fire. This is a photograph, or a couple of photographs, of the compartment floor, if you like, from above. So some rather large cracks there in the slab, a little bit bigger than you might be comfortable with normally. But again, the good news here is that the integrity of the compartment, the integrity of that floor wasn't infringed. So there wasn't fire spread from the compartment where the fire was taking place to the compartment above. And that was provided for by the metal deck and the mesh reinforcement to some extent. This is kind of a picture of the compartment below. So some fairly major deflections here, a total deflection of 925 millimeters in the worst position. But because there was no collapse, the test proved that the Broadgate fire, which happened during construction, wasn't a fluke. And what it proved as well is what the initial assumptions were, that there was some benefit from the continuous composite steel deck floors, and that they've got a lot more strength than is apparent from the tests that we've done, the single element tests. The information from those tests was also used by the Universities of Edinburgh and Sheffield. It was used by the BRE and Tata Steel's own research and development department to better understand the mechanisms of failure in fire, or rather how steel behaved in fire. And that eventually has distilled down into documents. So the knowledge from that fire test was consolidated, and you can find it in this document here. So changing tack slightly, and I'm now going to talk a little while about fire design standards. So some of you might be comfortable, and you might know BS 5950 Part 8, which was published in 1990. And that was the world's first standard for the design of steel structures in fire. And it's a relatively simple standard. And although that can still be used, it's now been overtaken by the Eurocodes. And there's various bits of information in the Eurocodes contained in different places. So this is some of them here, in the steel standards and the composite standards. The Eurocodes are more sophisticated in their approach, and they're a bit more extensive in terms of what they cover compared to 5950 Part 8. We also have a standard BS 7974, which outlines the actual process to be followed in the application of fire safety engineering for the design of buildings. I'm going to try and pick up on a little bit of the complexity contained in the Eurocodes, and that is the inclusion of an equation for something called time equivalence. So time equivalence relates the actual fire severity of the fire that actually takes place, taking into account the fuel loads, the ventilation, all those sorts of things, and then tries to track it back to our standard time temperature curve. So, for example, if the time equivalent for a fire in a compartment was calculated using this time equivalence of, say, 35 minutes, that would mean in a real fire in that compartment of calculated heat and duration would be equivalent to the standard fire for 35 minutes. I'm not sure if that came across very clearly. But really the point to take from that is that when you use the time equivalence methods, is that there's no fat. It's not a conservative approach, unlike the approved document. So this is the equation for the time equivalence from the Eurocodes. If we look at the UK National Annex, it very helpfully says that we can't use that equation, and it points us in the direction of something else, a PD document, PD 6688, which adopts a slightly more complex approach. But nevertheless, the Eurocode approach has become a standard part of modern fire engineering. It looks a bit complicated, but in practice it's relatively simple to use. But perhaps the most important point to make, though, is that it requires a little bit of knowledge and expertise in order to know which values to choose for entry to that equation. The final slide, or almost the final slide of my presentation. So this is, in closing, a case study a local case study, not too far from here in Glasgow. So this is Maxim Office Park, Eurocentral, just outside Glasgow, where the time equivalence method was used in the fire engineering of this project, or on many of the buildings. So 10 buildings in total. They obviously didn't use the English building regulations. They used the Scottish, if you like, variant. But again, if you looked at the technical standards in Scotland, what they told you is that many of the buildings on that site would have needed to be fire protected to 2 hours or 120 minutes. The engineer, which was Jeremy Gardner and Associates, did some analysis, and they used that time equivalence method. And when they compared that to the standard fire test, the actual fire period that they needed was just short of 30 minutes. Probably a little bit uncomfortable with that, or taking it too far, so they looked at different scenarios. They took the worst case scenarios, looked at unfavourable variations in terms of ventilation and fire loads and that sort of thing. And eventually where they ended up was that they engineered the fire period down from 120 minutes down to 60 minutes in most cases, and I think in one case it was 90 minutes. So that obviously had a big impact in terms of the passive fire protection used on the steelwork. And I think that's as much as I'd like to say. So thank you very much for your attention.